Under the cover of darkness, the world lies hidden from view. Without light, I've no idea what lies beyond my immediate surroundings. I'm closed in, enveloped on all sides by the unknown. For much of human history, when the sun went down and the dark set in, we were at the mercy of the night. But over the centuries, we've developed our own sources of illumination. We've lit our homes, our streets, our cities, and in doing so, we've banished the darkness into the shadows. And just as we've used light to illuminate our world, the more we've discovered about light's properties, the more of the universe it's shown us. We've seen into the depths of space and back to the beginning of time. But as we've looked deeper, we've come to realize how little we've seen, and that the cosmos's greatest mysteries remain hidden in the dark. Light and dark is essentially the story of everything we know and everything we don't know about our universe. And it all begins with light. It's such an integral part of the way we perceive the world, it's easy to take it for granted. But for centuries, understanding what light really is has been one of science's most enduring questions. The first steps towards understanding the properties of light were made in the 3rd century BC by the renowned Greek mathematician Euclid. And he did it by thinking about something so obvious that most of us don't give it any thought at all. Placing the tiny chair very close to the camera produces a large image on the retina. And because we're not used to seeing tiny chairs in everyday life, our brains are tricked into thinking it's a normal-sized chair in the middle of the room. And the reason this illusion works at all is because to judge distances, our brains rely on a simple fact. The further away things are, the smaller they appear to the eye. And it was by focusing on exactly why distant objects could appear the same size as much smaller ones closer up that led Euclid to discover one of light's most fundamental properties. Obviously, the London eye is much bigger than my fingers, I know that. And yet, to me, they look the same size. So how do we explain this? Well, Euclid came up with an elegant solution. For my finger to appear at the top of the wheel, my eye, my finger, and the top of the wheel must all lie on the same line. But Euclid's insight didn't just explain the tricks of perspective. It revealed a basic truth about light itself. Euclid had discovered that light travels in straight lines. Realizing how it travels marks the beginning of our scientific understanding of light. And it also meant that if we could divert it from its straight line path, we could change the way we see the world. But that leap wouldn't happen for another 2,000 years. It was eventually made in Renaissance Italy by one of the founding fathers of modern science. In the summer of 1609, Galileo Galilei made the short but fateful journey from his home in Padua to Venice, capital of the Venetian Republic. Galileo had flame red hair, a full beard, and was well known for his love of fine wines and generous hospitality, and also for his anti-establishment views. By this time, he'd also built up a reputation as a natural philosopher and mathematician, and he was regarded as a valuable asset to the Venetian Republic. But although, as a professor, he had a regular income, Galileo was never far from financial troubles. When his father died in 1591, Galileo, the eldest of 4 surviving siblings, became head of the household and effectively took on responsibility for supporting his brother, a poor itinerant musician, and for paying his sister's dowries. By the time he came to Venice, he still owed a significant amount of money to his 2 brothers-in-law, and so was always on the lookout for a money-making scheme. And that summer, Venice was abuzz with rumors of a device that appeared to do the impossible. A Dutch spyglass that could bring distant objects closer. It was just the opportunity Galileo was looking for. Back in the 17th century, the spyglass was cutting-edge technology, and details of how it worked were a closely guarded secret. All Galileo knew was that it consisted of 2 lenses arranged in a tube. And so when he developed his own, he kept it very secret as well. But we do know from a shopping list that he got his glass from the small island of Murano out in the lagoon. And because no tools existed, he had to improvise. For instance, buying an artillery ball to grind the curved surfaces of the lenses. It had been known since the first spectacles were produced in the middle of the 13th century that glass had the strange property of bending light. But unlike spectacles, the spyglass, an early telescope, required a combination of lenses in a very specific arrangement. This is how Galileo's telescope works. Rays of light come in from a distant object, so they're almost parallel, where they meet his first lens. This is the objective lens, and it's plano-convex, which means it's flat on one side and curved on the other. It's the sort of lens used to treat long-sightedness. What it does is bend the rays of light towards each other so that they would meet at a point. But before this focal point, Galileo places his second lens, the ocular lens, which is plano-concave. And this bends the rays of light back out again so that they emerge parallel where they enter the eye. And then the eye's lens focuses them on the retina. Now, the magnification of a telescope depends on the ratio of the focal lengths of the 2 lenses, the distances f1 and f2. The difficulty for Galileo was grinding down the convex surface of his objective lens to make it as shallow as possible in order to maximize the length f1, because the longer he could make that, the greater the magnification of his telescope. Produced in just a few weeks, Galileo's telescope had a magnification of 8 times and was far more powerful than the original spyglass. All he needed to do now was cash in on his new invention. Ever the showman, on the 21st of August, 1609, Galileo climbed one of the city's bell towers. Obviously, he'd have used the stairs. At the top, in front of an assembled group of Venetian noblemen and senators, Galileo demonstrated his telescope. It was a sensation. Using it, the Venetians would be able to see approaching ships 2 hours earlier than with the naked eye. The military and economic advantage of knowing who was sailing over the horizon was lost on no one watching that day. 3 days later, as a grand gesture, Galileo presented his telescope to the Duke as a gift. In return, he was guaranteed his job for life at double his salary. With his finances now secure, Galileo went on to develop a more powerful telescope. And with it, used the ability to bend light to change our perspective on the cosmos. This is the book Galileo published in 1610. It's called Sidereus Nuncius, which in Latin means the starry messenger. In it, he recorded his first observations of the night sky, the first anyone had ever made using anything other than the naked eye. Today, it's hard to imagine how anything contained in this little book was controversial. But you have to remember that back when it was written, the nature of the heavens was thought to be knowable only to God, and the Earth was considered to be at the center of the universe. These are his drawings of the moon. Since ancient times, all heavenly bodies were thought to be perfect spheres, but with his telescope, Galileo saw texture in the surface of the moon. Deep craters and mountains that, from the shadows they cast across the lunar surface, he estimated to be some 6 kilometers tall. As well as showing the heavens to be imperfect, his telescope began to uncover their true extent, revealing 10 times more stars than are visible to the naked eye. And in the final chapters, Galileo reports the discovery of 4 stars that appear to form a straight line near the planet Jupiter. His drawings show how their positions change from night to night. Although they moved, they always did so along the same straight line. And from that, Galileo deduced that they had to be orbiting Jupiter. They weren't stars at all. They were moons. Through his telescope, Galileo had seen evidence that overturned the accepted dogma that the Earth was the fulcrum about which everything in the universe revolved. Seeing moons in orbit around Jupiter meant that not everything went round the Earth. So, far from being the center of the universe, the Earth was just another planet. the telescope had allowed Galileo to glimpse the true nature of the cosmos and our place within it. But this way of manipulating light had another powerful application, one that would allow us to see into another world. In 17th century London, one of the most prominent scientists of the age was using lenses in a very different way. Robert Hooke had taken the basic principle of the telescope and used it to build a microscope.
Galileo uses the telescope to discover a new world in the heavens, and Hooke uses the microscope to discover a new world in the very, very small. But there's a difference, because what Galileo had presented was a world that was bigger and more plentiful, but it was a world that people were at least vaguely familiar with, because you can look up in the sky and see the stars. Whereas the world that Hooke presented was really something spectacular and new. It was a world inside the tiniest particles of matter that no one had ever imagined to be there before. People didn't even realize that there was a microscopic world there to reveal.
Hooke trained his microscope on a huge range of materials and living things. But it was his drawings of the exquisite detail he saw in the bodies of insects that would become famous.
So up here you can see a human flea, Pulex irritans, a very tiny creature. And then here we've got the plate from micrographia, which is a huge image of the flea that Hooke produced. And it's really something spectacular. And this would have folded out in the book, so it was really very large. Some people said it was as big as a cat.
It's a work of art, really. I mean, there's just so much intricate detail in there.
It is, and there was nothing like it before Hooke. They really were unprecedented. And the shading and the quality of the images is just superb.
And it's accurate. I mean, it's...
It is. It's absolutely accurate. I was looking yesterday at images of photographs of the flea, and there's really, actually made with an electron microscope, and there's really nothing to choose between Hooke and the current images. This is an image of the compound eye of a fly, which Hooke shows in amazing detail for the first time. And this is an image of the foot of a fly. Hooke shows you the foot has little spikes in it that allow it to clasp into the pores on a surface.
Now, this image looks less interesting, less intricate than the others.
Well, it doesn't look terribly interesting, but actually it's really quite a profound picture, because what Hooke is looking at here is a very thin slice of cork, which he cut with a penknife, and he's looking at the little individual components that make it up. And he calls them pores, and then he calls them caverns, he calls them boxes, and then he calls them cells. And cell, of course, is the term that stuck. These are the little constituent parts, not just of cork, but of all living things. And so it's actually a profoundly important discovery, and a name that has become standard in biology.
Using glass to bend light revealed our true place in the universe. And the intricate architecture of the microscopic world.
The more we looked, the more we saw. With each new insight into the nature of light came a fresh understanding of the cosmos. And the next discovery would take us far further and enable us to read the story of the stars. And it began with something Hooke had glimpsed through his microscope. This is Robert Hooke's book, The Micrographia, published in 1664, 350 years ago. It's full of his famous diagrams. Here's his picture of the flea. It's incredible seeing it in its original form. It really is the size of a cat. These images really captured the public imagination and they made the book a sensation. But for me, the Micrographia is about much more than that. The chapter that interests me as a physicist is one that contains hardly any images at all. And it's this one here, of the colours observable in Muscovy glass and other thin bodies. Here, Hooke describes the iridescent patterns of rainbow colours he sees through his microscope as light passes through thin materials, like soap bubbles and Muscovy glass, a silicate mineral that's made up of lots of thin layers. At the time, it was thought that white light, like sunlight, was pure, that it came directly from God. And so Hooke concluded that the colours he was seeing must have somehow been added to the light, that they were effectively created as the light passed through the materials. But Hooke's theory about coloured light was about to be challenged by his greatest rival. Isaac Newton is one of the world's most revered scientists. Best known for his theory of universal gravitation. And just like his laws of gravity, Newton's discoveries about the nature of light are among his most celebrated achievements. But the story of how that work began is much less familiar. And this time, there was no fruit involved. This is Stourbridge Common, a sleepy riverside meadow on the banks of the River Cam. But when Newton visited in 1664, it would have been very different. For over 700 years, every September, this place would be transformed into what was, at its height, the largest fair in Europe. For several weeks each year, people would descend on the common for an annual festival of commerce and debauchery. This whole common would have been packed with makeshift stalls. Farming produce, brandy houses, goldsmiths, silk merchants. There'd have been slack rope dancing, puppet shows, music, temptations of every kind, packed into row upon row of wooden booths and tents. Stourbridge Fair was a place you could buy anything you could imagine. But when Newton came here, it's said he bought just one thing, a prism. He bought it because it performed the same magic Hooke had seen with his microscope. Newton would later write that using his new purchase, he would try the celebrated phenomena of colours.
a rather understated introduction to work that would produce one of the most profound insights into the nature of light. Newton devised an ingenious experiment to discover precisely how these rainbow colours were produced, and to put Hooke's theory that they were created by the prism itself to the test. This is Newton's own drawing of what he called his crucial experiment. In it, he arranged a prism so that sunlight coming in from a small hole he'd made in the shutters of his bedroom window passed through it and projected coloured light onto a screen. Well, here's my light source, and here's my prism, which if I arrange carefully, I can get projected onto the back pillar. Of course, none of this was new. People knew that prisms produced coloured light, but what Newton did next had never been done before. He first isolated one of the colours using a slit. So, in this case, the orange light. He then passed that orange light through a second prism. Now, if Hooke was right, then this prism should add the other colours to the orange and reproduce the rainbow. But all Newton saw was orange light. The prism wasn't adding any extra colour. He concluded that the colours must have been contained in the white light in the first place, that white light wasn't pure and prisms don't add anything to it. Instead, they split it up into its constituent parts. Newton named the colours that make up white light the spectrum. And when this discovery was combined with the telescope, it would show us something remarkable. The spectrum would reveal precisely what it was we were looking at out in space. This is a spectroscope. As sunlight comes in, it's broken up into its constituent colours and spread out much more finely than you'd get with a simple prism. Now, with this camera, I should be able to show you what I can see. I'll just check that it's working. Yes? Okay. When scientists first did this in the middle of the 19th century, placing the spectroscope on top, they saw something completely unexpected. You can see the colours of the spectrum as Newton would have seen them. But if you look more closely, you can see something else. It's not continuous. It's broken up by lots of thin black lines. These are gaps in the spectrum. It was soon realised that these gaps were due to atoms in the outer atmosphere of the sun absorbing certain wavelengths of light coming from its interior, and that they could be used to work out the chemical composition of the sun. Every element absorbs a unique pattern of wavelengths, an optical fingerprint that can be used to determine the chemicals that make up any bright object you can see in the sky. And in Rome, one man was using this technique to study light whose origins lay far beyond the sun. Father Angelo Secchi was no ordinary priest. He was charismatic and viewed as something of a heretic by his fellow Jesuits. And that's because he was also a professor of physics with an evangelical passion for astronomy. In 1852, Secchi was appointed director of the Vatican Observatory. And within a year, he'd built a new observatory on the roof of St. Ignatius Church in the heart of the city.
At the time, most astronomers were interested in mapping the positions of the stars and charting their motions across the heavens. But Secchi was different. He wanted to know what they actually were. So, from his vantage point high above the streets of the Eternal City, he began to meticulously analyze their light. Fitting a spectroscope to the observatory's telescope, Father Secchi laboriously recorded the spectra of more than 4,000 stars. This is Secchi's book, La Stella, The Stars, which he published in 1877. And flicking through it, you can see many of the observations that he made. This one in particular is interesting. It shows some of the spectra he recorded. The top one here is from the sun, but the second one is starlight. It's from Sirius A, the dog star, which is the brightest star in the night sky. It's 8.6 light years from Earth and over 20 times as luminous as the sun. You can see from its spectrum this clear sequence of bands, which is the signature of hydrogen, because it's a relatively young star. The universe's hottest, brightest stars have spectra rich in the two lightest elements, hydrogen and helium. But as they age, they cool, and their spectra reveal the presence of many heavier elements. This third one is from the star Betelgeuse, which is a red supergiant. It's near the end of its life, and so you can see from the many bands here that it's composed of lots of different elements. What's remarkable about this image is that, it really is one of the key moments in the history of astronomy, that we can learn so much about what distant stars are made of just by examining their light. But because Secchi had catalogued the spectra of so many stars of different ages, his observations led to something even more profound. That by analysing starlight, we can determine the stars' life cycles. When they were born, and when they'll die. Understanding the spectrum had allowed us to read the story of the stars. It's quite incredible to think that what began as a simple experiment in a darkened room could reveal so much about the universe. That the scant light from those tiny points in the night sky could contain within it the epic drama of the heavens. But that wasn't all the spectrum could tell us. Today, we know that it's made up of light of many different wavelengths, and that those wavelengths extend way beyond the range we can see. The spectrum, from the longest wavelengths used in radio communications to the very shortest wavelength gamma rays, covers a range of 30 orders of magnitude. The longest are 1 followed by 30 zeros bigger than the shortest. That's the same as a spread and range of weights, from that of a single grain of sand to the weight of all the water in all the oceans on the planet. And within that vast spread, visible light, the frequencies we can see,
covers a factor of just 2. That's the same as the difference in weight between this pebble and one twice its size.
Are we all set, Doctor?
Yes, I think so.
And throughout the 20th century, opening our eyes to the full spectrum revealed even more of the universe.
If you had infrared eyes, here's how the sky would look.
Infrared allowed us to see the universe's coolest stars, while radio telescopes, sensitive to the longest wavelengths, revealed a cosmos in turmoil.
It's the violent events that are picked up, exploded stars and galaxies.
And satellites have scoured the heavens for short wavelength ultraviolet.
The OAO picks up the ultraviolet light from hot stars, which the atmosphere cuts off from ground telescopes.
And here's the very latest window, gamma rays, which are like very energetic X-rays.
Seeing beyond the visible has allowed us to peer deep into the cosmos.
I was cock-a-hoop about this.
I too was wildly excited when I heard of this discovery.
But the very fact that light had proved such a useful tool for exploring the universe depended on one of its most mysterious properties. Light behaves like a wave, but if it is a wave, what is it a wave in? Waves are carried across the ocean by the water, and the sound you can hear now is due to waves in the air. In the vacuum of space, there is no air, so there is no sound. But the reason you can see me is because I'm lit by sunlight that has traveled 150 million kilometers through empty space. So what is light? And how can you have a wave in nothing? Answering that question would not only reveal what light is, it would ultimately allow us to glimpse the beginning of the universe. And the first part of that solution was a discovery that challenged our most basic assumptions about how we see the world. To our eyes, light appears to be everywhere instantaneously. As I look out at the view, there seems to be no time lag, no delay while I wait for the light to reach me. But towards the end of the 17th century, it was discovered that our senses are mistaken. In 1672, the Danish astronomer Ole Rømer arrived in Paris to begin work at the city's observatory and to continue his observations of the moons of Jupiter. For more than a decade, Giovanni Cassini, the observatory's director, had been documenting their orbits in minute detail. Jupiter's innermost moon, Io, is known to make a complete circuit around the gas giant once every 1.77 Earth days. That's every 42.5 hours. Now, from Earth, we can see it disappear behind Jupiter and then re-emerge around the other side as it travels around in its orbit. But here in Paris in the 1660s, Giovanni Cassini had noticed that the timing of these eclipses seemed to vary, sometimes sooner, sometimes later than expected. Soon after he arrived in Paris, Rømer noticed that these fluctuations weren't happening at random. When the Earth was closer to Jupiter, Io would be seen to disappear and re-emerge earlier. But as the year went by and the Earth moved in its orbit around the Sun so that it was further away from Jupiter, then the eclipses appeared to happen later than expected. Romer knew the Moon always took the same time to travel around Jupiter. His great insight was to realize that the variations were due to the fact that light itself takes time to travel through space. Here's how it works. The eclipses of Io appear later than expected when the Earth is further from Jupiter because light takes a longer time to cover the greater distance. But they appear earlier when the Earth is closer because light needs less time to reach the Earth. Light isn't instantaneous. It travels at a finite speed. Today, we've not only measured light's speed with incredible accuracy, we've seen it in motion. This is a video made by scientists at MIT using a camera designed to monitor extremely fast chemical reactions. It has a shutter speed of around a picosecond. That's a millionth of a second. The time it takes light to travel just a third of a millimeter. Now, look what happens when I press play. What you can see here is a pulse of laser light moving through a water-filled bottle. To us, this would appear as the briefest of flashes. But the camera reveals how the pulse travels through the bottle, scattering and bouncing around as it hits the water molecules. Light travels so fast, 300,000 kilometers per second, that slowed down by the same amount, a bullet would take an entire year to travel the length of the bottle. It's one thing to know that light travels at a finite speed, quite another to actually see it move. The discovery of the speed of light was hugely significant. Not least because it proved crucial to uncovering what light actually is. Born in the summer of 1831, James Clerk Maxwell would become one of the leading lights of 19th century physics. His work on electricity and magnetism was one of the greatest achievements of the age. This is Glen Lair in southwest Scotland, Maxwell's family home. While he was growing up here, he developed an insatiable curiosity about the world around him, a desire to understand nature that he would never lose. The young Maxwell seems to have taken great delight in tormenting his parents and his nanny by constantly asking them how things worked. "What's the go of that?" he'd say. And if anyone ventured an answer, the young Maxwell would only be satisfied for a moment before asking them how they knew. Of course, none of this is particularly unusual for a child, but what sets Maxwell apart is that he was just 14 years old when he wrote his first scientific paper. So young that a friend of the family had to present it to the Royal Society of Edinburgh on his behalf. Maxwell was one of the greatest scientists who ever lived,
and it was here that he carried out his most important work.
During the 1860s, Maxwell produced a virtuoso piece of mathematics that showed electricity and magnetism were different aspects of the same thing. But his calculations would show something else. Quite by accident, they would reveal the true nature of light.
These are Maxwell's 4 famous equations that describe the relationship between electric and magnetic fields. Curl of E is minus dB by dt. E is the electric field, B is the magnetic field. Curl of B over mu naught div of E equals 0 equals epsilon naught equals naught. With a bit of algebra and manipulation, these 4 equations can be combined to give one single equation. So the way it's done is like this. We take curl of E.
Hidden deep within his mathematics was something that even Maxwell didn't expect.
Minus del squared E epsilon naught rad d2 div. This second term is 0, and I'm left with del squared of E minus mu naught epsilon naught d2E by dt squared. This is the wave equation. It tells us how an electromagnetic field travels through space. Now, the important bit is this here, mu naught epsilon naught, because it's related to the speed that the wave is traveling. In fact, the speed is given by 1 over the square root of mu naught epsilon naught. And if you work that out, you arrive at 3 times 10 to the power 8 meters per second, or 300,000 kilometers per second, the speed of light.
If electromagnetic waves moved at the speed of light, it could only mean one thing.
Maxwell knew this had to be more than just a coincidence. It meant that light itself had to be an electromagnetic wave.
The discovery that light is an electromagnetic wave explains one of its most puzzling properties.
What Maxwell's equations show is that light consists of electric and magnetic waves traveling through space. So light is simply electric and magnetic vibrations feeding off one another as they move. And we now know that these electromagnetic waves have a remarkable property. They don't need to be waves in anything. They can travel through empty space. I remember first learning about this when I was in my second year at university. I was in lecture hall 33 AC21 of the physics department at the University of Surrey. The lecturer was Dr. Chivers. And I remember turning to my friend next to me and remarking on how incredible I thought this was. And I could tell by his reaction that he thought I was a bit of a geek. But actually, it is incredible that in just a few lines of algebra, you can tell what light really is.
And the fact that light travels at a finite speed has enabled us to do something else. It allows us to look into the past.
Looking at a mirror 1 meter away, you see yourself as you were 6 nanoseconds ago. From Earth, the moon appears as it was 1 second ago, and the sun 8 minutes in the past. The further you look out in space, the further you look back in time.
Light from the cosmos's most distant objects has taken billions of years to reach the Earth. But there's one source that has taken us so far back in time, we've reached the very limit of what can be seen with light. In 1964, while converting a strange-looking horn antenna designed for early satellite communications to make astronomical observations, Arno Penzias and Robert Wilson began to pick up a mysterious signal they couldn't explain.
Here we had purposely picked a portion of the spectrum, a wavelength of 7 centimeters, where we expected nothing, or almost nothing, no radiation at all from the sky.
Instead, what happened is that we found radiation coming into our antenna from all directions. It's just flooding in at us, and clearly was orders of magnitude more than we expected from the galaxy.
At first, they dismissed it as noise, something unwanted generated by the antenna itself.
Now, we had some suspicion because the throat of the antenna came into the cab and was a little bit warmer. And that was an attractive place for pigeons, at least a pair of pigeons who like to stay there, especially in the cold winter. We didn't mind that because they flew away when we came, except that they had coated the surface with a white sticky material which might not only absorb radio waves, but then emit radio waves which could be part or maybe all of our result.
With the antenna cleaned and the pigeons, well, it didn't end very well for the pigeons. Penzias and Wilson began searching for an astronomical explanation. But the signal wasn't coming from anything in our own galaxy, nor did it appear to be coming from any other galaxy. It seemed to be coming from everywhere.
No matter when we looked, day or night, winter or summer, this background of radiation appeared everywhere in the sky. It was not tied to our galaxy or any other known source of radio waves. It was rather as if the whole universe had been warmed up to a temperature about 3 degrees above absolute zero.
And so we were left with the astonishing result that this radiation was coming from somewhere in really deep cosmic space, beyond any radio sources that any of us knew about or even dreamed existed.
What they discovered was light so ancient it had been stretched out into microwaves and cooled to just a few scant degrees above absolute zero. Light that had been traveling to Earth for almost the entire age of the universe. It hadn't come from a distant galaxy, and it was far older than any star. Penzias and Wilson had discovered that the entire universe was awash with light from the embers of the Big Bang itself. Called the cosmic microwave background, it was released when the universe was just 370,000 years old. And it gives us a snapshot of the cosmos in its infancy. And here it is, the latest image of the cosmic microwave background, taken by the Planck satellite and published in early 2013. The different colors are fluctuations in temperature in the early universe, and the information they contain has proved priceless to cosmologists. The tiny variations in temperature are caused by matter clumping together into what will eventually become stars and galaxies. But what's truly remarkable about this image is that it's not just light from the early universe. It's the very first light there ever was. During the first era of its life, the universe was a fireball of hot, dense plasma that trapped light, preventing it from moving. Then, as the cosmos cooled, the plasma condensed, forming the first atoms. And the first light that would become the cosmic microwave background, was released into the universe. It's sort of hard to express what an astonishing achievement this is, that from our small planet, orbiting an unremarkable star, we've reached out into the universe and seen as far as it's possible to see with light. The discovery of the cosmic microwave background appeared to complete our picture of the universe. The final chapter in our use of light to explore the cosmos. Understanding the nature of light has allowed us to illuminate our world. We've captured it from the depths of space and the beginning of time. At the smaller scales, light has uncovered the microscopic structure of living things, and at the largest, it's shown us our place in the cosmos and told us the story of the stars. Virtually everything we know about the universe, we know because it's been revealed by light. But just as it seemed light would lead us to a complete understanding of everything, in the last 30 years, it's shown us something disturbing. The vast majority of the cosmos can't be seen at all. Far from being a universe of light, much of it is hidden in the dark. Next time, how scientists came to the realization that more than 99% of the universe lies concealed in the shadows, and the extraordinary quest to uncover what's out there in the dark. Whether you want to step into the light or explore the mysteries of the dark, let the Open University inspire you. Go to bbc.co.uk/light and dark and follow the links to the Open University.
Planet Earth, where speed is in demand, the fastest people, vehicles, and technologies seem to crawl in a cosmos where light speed is king. More than king, the speed of light is the cornerstone on which the universe is built.
There's a famous saying in physics, which is that the speed of light is not just a good idea, it's the law.
The speed of light is one of the most important speed limits in the entire universe.
The speed of light, 186,000 miles per second, is just incredible. I mean, if light traveled in a circle around the Earth, it could circle the Earth 7 times in 1 second. That's an incredible speed.
That incredible speed is the first thing we encounter when confronting the phenomenon of light. To say it is fast is a colossal understatement.
It's amazing to me that when I talk on my cell phone, I can talk to somebody clear across the country, and I'm not really aware of any time lag. And that signal is going from my phone to a tower, up to a satellite, back down, and it seems instantaneous. So we really take for granted the speed of light could practically be infinite to us.
Physics professor Clifford Johnson of USC is an avid bike rider. Circling a track, he considers trying to cover the same 186,000 miles that light does in 1 second. He'll find, however, that his work will be cut out for him.
To travel the distance that light moves in just 1 second, it would take me 22 months on a bike moving at 12 miles an hour, cycling 24 hours a day.
But the speed of light, in relation to the speed of life, makes our world work in just the way we've come to expect.
One of the beneficial effects for humanity of having the speed of light be as fast as it is that what you see is what you get.
Light speed makes everyday experience virtually instantaneous. When the light bulb goes on, you see it right away. Anything that happens around you registers immediately. And certain experiences make it crystal clear that light travels faster than anything else, including sound.
One interesting consequence of the great speed with which light travels is that you see a flash of lightning essentially instantaneously, but you hear the thunder only later on.
But light speed has its limits when stacked up to a place as large as the universe.
We think that the speed of light is unimaginably fast on a human scale. However, in astronomical terms, it's actually kind of pokey.
And so it's ironic that when the Apollo spacecraft blasted into space, traveling at what seemed an amazing 25,000 miles per hour, the speed of light proved frustratingly slow when it came time to talk to astronauts 236,000 miles away on the lunar surface.
So when the astronauts were on the moon and people asked Neil Armstrong, "Hey, Neil, what's it like up there?" Several seconds went by between the question and Neil Armstrong's answer.
Neil, this is Houston, radio check, over. Hi, Roger. Houston, loud and clear. Roger, loud and clear, Houston. Roger, bud.
And those several seconds were not because he was thinking about the answer, but rather because it took 1.3 seconds for the signal traveling at the speed of light to reach Neil from mission control, and another 1.3 seconds for his reply using radio waves to come back. And that's 2.6 seconds without even thinking.
Okay.
The 1.3 seconds it takes light to travel from the Earth to the Moon is pocket change compared to other celestial bodies. Light from the Sun, for instance, takes more than 8 minutes to get to the Earth.
If the sun were to disappear right now, if the sun were to suddenly vanish, it would take 8 minutes before we would even feel the shock wave and see the effects of a disappearing sun.
The limits of light speed also make communicating with Earth's far-flung spacecraft a special challenge. It takes up to 44 minutes for signals to travel back and forth to the probes exploring Mars. More than 3 hours to Cassini at Saturn. And over 29 hours to Voyager 1, the most distant of all, now heading out of the solar system. Still, these distances are trivial on a cosmic scale. We can almost understand the 10 billion miles separating Earth from Voyager. But what's next? The nearest star is a red dwarf named Proxima Centauri, nearly 25 trillion miles away. That's 25 followed by 12 zeros.
I am often asked a question, how can you as an astronomer really comprehend these vast distances, these huge numbers? And the answer is, I can't. The human brain really doesn't wrap itself around numbers that big. Occasionally, I actually write out how many zeros there are in kilometers from here to a galaxy, just to see how huge that number is. But in reality, of course, as astronomers, we would be spending all day writing zeros unless we came up with a better unit to use. And that's what a light year is. A light year is approximately 6 trillion miles. It's the distance that light travels in 1 year.
Using light years to describe distances opens up another dimension of light speed's character. Think of it. Sirius, the brightest star in the sky, is 8.6 light years away. That means we see it not as it is today, but as it was 8.6 years ago. We see the bright star Vega as it was 25 years ago, and the red supergiant Betelgeuse as it was 500 years ago.
It's a wonderful gift of nature that because it takes time to travel, we're able to look back in time. The further out we look in distance, the further back in time we look. We would have no idea what our cosmic history was if the speed of light traveled instantaneously.
Laura Danley is curator of the historic Griffith Observatory in Los Angeles. With light's ability to take us into the past, she's assembled a stack of photos that tell light speed's story of the universe in snapshots, looking back in time to its beginning, more than 13 billion years ago, to the present day.
I'm putting together a scrapbook of the history of our family of galaxies, and that shows all the galaxies that we can see with our telescopes as far back as we can see with our telescopes.
Each photo in this album, then, shows something in the universe with a look-back time equivalent to its distance in light years. The famous Crab Nebula, 6,500 years ago. The galactic core, center of the Milky Way, 26,000 years ago. And the Andromeda Galaxy, our next-door neighbor, 2.5 million years ago. But practically yesterday on a cosmic scale.
I love this cluster.
For almost 90% of the look-back time, the album is filled with common galaxies. Common, yes, but intriguingly diverse.
These two are colliding. You can see one going what appears to be right through the other. And there's a lot of drama in the way galaxies evolve and the way they interact with one another. So this one would be, it's only about 500 million light years away.
As Danley places each shot in the album, a bigger picture begins to emerge. Adult galaxies have been the main characters, evolving in all their variety for the past 12 billion years. But the cosmos also has its childhood photos, showing galaxies when the universe was a mere toddler.
These are actually very interesting galaxies at about 11 billion light years away. These compact galaxies represent what might be a two or 2.5-year-old child, just really learning how to walk.
But even these galaxies have their younger brothers and sisters. This spectacular shot shows a gravity lens, a cluster of galaxies 2.2 billion light years away that bends light, allowing us to see much further in space and time. The lens reveals a tiny speck identified as one of the earliest galaxies we can see, as it was 13 billion light years ago, still an infant in the evolving universe.
Galaxies, when they were babies, really don't have a lot of distinguishable features. They're kind of blobs. They don't really have a lot of structure.
The universe as a whole was something of a blob at the beginning of its life, too. What we see of that time are the first light waves in history, reaching us only now, 13.7 billion years after they flashed into existence. We see them in the picture of an afterglow from the Big Bang. And they are known today as the cosmic microwave background radiation,
The cosmic microwave background radiation is the most distant thing we can see. It is, in a sense, the picture of the baby upon delivery.
NASA's all-sky picture reveals a glow that is uniform everywhere we can see. The universe as it was in a cosmic moment after its birth. But here, our view comes to a sudden halt. What we can see of the universe is limited, not by the size or power of our instruments, but by the barrier of light speed itself. How can the fastest thing in the universe make us blind to the infinity of space? Knowing that light speed is 6 trillion miles per year gives us the light year, a convenient shorthand for talking about the huge distances in the universe. But it's just as important to understand that light speed at 6 trillion miles per year is an ironclad constant.
The speed of light is so constant that the universe actually changes everything so that you never see it going any other speed. So the speed of light really is the measuring stick of the entire universe.
In fact, the constancy of light speed results in an amazing tool for measuring distance in the vastness of space. The tool is called redshift. It happens as light between galaxies travels at a fixed speed. When the space between the galaxies expands, the light racing between them gets stretched, turning red in color.
As light goes from one galaxy to another, from a distant galaxy to our own, for example, that light gets stretched along with the stretching of space. And that causes intrinsically short wavelength light, like blue light, to gradually become long wavelength or redder light. That fundamentally is the cause of the redshift that we see in the spectra of galaxies.
How does the redshift turn into a way to measure distance? It's all because of an astonishing discovery made in 1926 at the Mount Wilson Observatory outside Los Angeles.
Being up here on Mount Wilson is always a thrill for me because it was actually right here at this location that our view of the universe entirely changed. It was here that Edwin Hubble found out the universe is expanding. And that was an amazing thing. He wasn't expecting it. Nobody thought that was the case. And it changed everything.
Seeing red shifts everywhere, Hubble found that all of the universe's galaxies were moving away from each other, which we now know is caused by the expansion of space itself. As seen from the Earth, a galaxy doesn't look like it's moving away, but we know that it is because its light is redshifted. A galaxy moving away at low speed has a slight redshift. A galaxy moving faster has a larger redshift. But Hubble found that those faster-moving galaxies are also farther away. That meant the greater the redshift, the more distant the galaxy. By seeing how fast space is expanding and working the math backwards, cosmologists have been able to estimate the age of the universe. Combine that with light speed, and you have a major brain twister.
The universe is such a huge place that the light travel time really becomes important to us. We believe the universe began about 13.5 billion years ago. That means the farthest in any direction we can look is 13.5 billion light years. There hasn't been enough time for light to travel more than that.
It's called our light horizon, a sphere 13.5 billion light years in all directions, containing everything we can see. But that's where the brain twister comes in. Does space end there?
We have no reason to believe that the distance we can see is the entire size of the universe. In fact, it might be much bigger than that. It's just that with light travel time, that's all we can see. That's our horizon.
So consider this conundrum. Astronomers in a galaxy at one edge of our horizon can't possibly see any galaxies on the other edge of our horizon. But they can see galaxies 13.5 billion light years in the other direction. And so can astronomers at the edge of their horizon, and on, perhaps to infinity. As for astronomers on Earth, light speed has them trapped.
If we ask what is happening beyond our light horizon, we have to face the fact that the speed of light really is a barrier. We've never seen anything beyond our light horizon.
Can we take comfort in the fact that there is so much to see inside our horizon? This breathtaking shot is the Hubble Space Telescope's ultra-deep field. It's a massively detailed photo of an area of the sky 100 times smaller than the full moon, yet containing 10,000 galaxies, some whose light has been speeding toward us for 13 billion years. Beyond that is the cosmic background radiation from just 400,000 years after the Big Bang. In NASA's color-coded picture, the radiation's glow is pure green, representing a distribution of matter so uniform, its temperature varies no more than 1/50,000th of a degree. Nothing in human experience is even close to this kind of uniformity. In fact, astronomers believe the universe should really be very different.
By rights, the universe should be lumpy. If you look in this direction and you look in that direction, you should see two entirely different concentrations of matter, different temperatures, but it's extremely uniform. Therefore, we have a puzzle.
The puzzle has its roots at the universe's birth in the Big Bang. If everything flew apart from the beginning, why shouldn't it be uniform?
No kind of explosion that we know about leads to that kind of uniformity. If you imagine an ordinary explosion, an atomic bomb, a piece of TNT, it's not really uniform at all. There's a piece of shrapnel going off there, a piece of paper going off there, an extra piece of iron going off there. It's really very non-uniform.
So scientists believe the cosmic background radiation just shouldn't be as smooth a green as it is. We can find out why in an ordinary paint store.
Let's consider a universe that consists of different color cans of paint. In our hypothetical paint universe, we have a can of yellow paint and a can of blue paint. And at the instant of the Big Bang in this universe, two cans of paint start expanding apart from each other. In our hypothetical paint universe, one side of it would look yellow, and the other side would look blue.
But as we've learned, the cosmos looks green, whether it's the paint universe or the real thing. The two colors of paint represent the different particles in the infant universe. To end up a uniform green, like the cosmic background radiation, they had to be touching. But when scientists first calculated the speed of the Big Bang, they concluded that it blew everything apart faster than the speed of light, meaning blue and yellow were too far apart, even at the instant of creation, for any mixing to take place.
Seeing a universe that's so uniformly green would be very strange. It would be like taking our can of yellow paint, pouring it out, and having it be green, then taking the can of blue paint, pouring it out, and having it be green as well. It's impossible.
This horizon problem can be solved by a theory that I've worked on called inflation, which is a twist on the Big Bang.
Inflation is now the widely accepted variation that makes the Big Bang work without the limit imposed by the speed of light.
Another way this could have happened is that our paint universe might have expanded only this far. The two cans of paint have enough time to mix and become uniformly green before the universe undergoes a sudden period of expansion that occurs faster than the speed of light. This would spread green paint all over the universe.
If this theory is right, the period of inflation is really the Big Bang that we observe. The other bang that happened before that becomes really a little bang. It's just a precursor to the real Big Bang.
Even today, the universe is expanding at high velocity, galaxies speeding away from each other so fast that they seem to violate light speed as the ultimate speed limit. The faster-than-light expansion of space sets yet another limit on what we can see from Earth, where the galaxies of the universe continue to rush away from us.
The galaxies that are relatively near to us, those that you can see easily, are moving away pretty fast. And indeed, the more distant ones are moving away faster. But the ones that are really far away, in fact, are moving away faster than the speed of light. And then there are the galaxies that you will never see because they started out so far away that the light from them will never reach you because the space is expanding faster than the speed of light.
Space itself, then, is the exception to the rule. It can expand faster than the speed of light, but everything inside it remains bound by Albert Einstein and his theory of relativity.
Albert Einstein is the cop on the block. You cannot break the light barrier. We physicists can accelerate particles to 99.9999% the speed of light, but we have never, ever broken the speed limit.
But we don't need to break the limit to experience the strange province of light speed. If the universe bends and stretches around the speed of light, what happens when we hit the accelerator and start to get close? For most of us, light seems simple and uncomplicated, a quality of nature by which we see the universe. Under the scrutiny of science, however, it becomes strange and bizarre.
Light is such a common thing in our everyday experience, and yet we have very little understanding of it, really. It's very weird. The speed of light is something that the entire universe bends around to accommodate.
We can begin to understand why the universe bends itself around light speed by joining physicist Clifford Johnson at a bicycle track, where a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, and it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while he's standing still. It lands roughly halfway down the track. Next, he'll throw the ball again, but this time from a moving bike, with different results.
If I throw the tennis ball at that same speed while riding the bike, it'll go faster because it's the speed of the tennis ball plus the speed of the bike, and so it'll go further.
Compare the two tosses, and the difference is clear. The ball goes faster and farther when thrown from the moving bike. It makes perfect sense. But now we put light to the same test, using the bike's headlight instead of a tennis ball.
If I'm standing stationary and I switch on the headlight of the bike, that beam of light that comes out of the headlight comes out at the speed of light. No other speed but the speed of light.
Suppose the beam was slow enough for us to actually see its motion down the track. We mark its position just a brief moment later. Next, Johnson switches on the headlight at riding speed, and the unexpected happens. In that same moment of time, the light travels exactly the same distance as before.
Unlike for the tennis ball, you don't add the speed of the bike to the speed of the light. The speed of light remains the speed of light.
The two light beams travel the same distance because light speed is constant and independent of the source's motion. It may fly against intuition, but it is a fact of nature. Every beam of light in the universe travels at the same speed in empty space, no matter how fast the star or comet or galaxy that emits it is moving. After scientists discovered this fact at the end of the 19th century, Albert Einstein did the math for the rest of us and developed his special theory of relativity, with constant light speed as its center.
Understanding the speed of light gave us a window into understanding the nature of space and time as we understand it now. We do not live in a rigid world where meter sticks and a clock ticking at irregular intervals. We live in a flexible, stretchy, Einstein's world, relativistic world of space and time.
In common experience, the universe doesn't seem very stretchy to us because compared to light speed, we are moving very slowly. But when we crank up the velocity, things begin to change.
As you get closer and closer to the speed of light, all sorts of strange and marvelous distortions take place.
When we say that the universe kind of bends itself so that the speed of light is always constant, it's amazing how literally that's really true. As you move closer and closer to the speed of light, your time appears to slow down to an observer that's just sort of watching you go by. That's amazing.
When Clifford Johnson bikes around the track, he needs to be going about 56 million times faster than his current 12 miles per hour to get close to light speed. But suppose he could.
Imagine I were riding my bike close to the speed of light. Never mind whether that's possible or not. Just imagine that this was happening. my clock's running slow compared to the cameraman on the ground who's filming me. If I do that for a while, I'm going to age much more slowly than the cameraman who's on the ground. So that when I come back from the trip and come back and talk to the cameraman, he's actually much older than when I left him.
If this sounds like magic instead of science, there is proof in something that many of us experience every day.
A great example of Einstein's special theory of relativity and the fact that clocks that are moving relative to you run more slowly than your own clock, which is at rest, is the GPS system.
The global positioning system lets us drive our cars without getting lost.
Turn right.
GPS begins with a network of 24 satellites orbiting the Earth 12,500 miles above the surface. At any one time, the device in your car receives signals from at least 4 satellites and compares their light speed travel times to calculate an accurate location on the ground.
Drive 500 feet, then turn right.
The whole thing depends on super accurate clocks. And when the engineers designed the system, they knew the satellites would be orbiting at nearly 7,000 miles an hour. The speed is enough to slow down their clocks by a tiny fraction of a second. The engineers have factored all the relativistic time differences into the system, which gives it impressive precision.
If the clocks in the satellites are running at a different rate than the clocks down here on Earth, and you don't take that into account, you will get the wrong answer for where your car is.
Drive 0.1 miles to destination on left.
The distortion of time is only one of the strange results of traveling close to the speed of light. On the bike track, Clifford Johnson continues to push the envelope as space begins doing odd things to him and his bicycle.
Imagine I'm on my bike again, going close to the speed of light. An observer looking at me would actually see, for example, that the length of my bike in the direction of motion I'm moving is getting shrunk. Actually, the bike is getting shorter.
The effect is called length contraction, and together with time dilation, it is seen by a stationary observer while looking at someone traveling close to light speed. But Professor Johnson does get his own chance to witness light speed's weird effects. As his velocity closes in on light speed, his view of the world changes drastically.
What I'm seeing as I move close to the speed of light, straight ahead, is that the shapes in front of me are getting quite distorted as compared to everyday life. Everything is being twisted into a sort of tunnel shape, and the colors are getting distorted in various ways.
The color changes come from the Doppler effect, and the shape distortions from a phenomenon known as aberration.
The distortion is somewhat similar to what you would see if you were driving through a rainstorm. If you were stationary, you would just see the rain coming straight down if you looked out of the side of the window. Whereas if you were moving through the storm, you would see that the rain appears to be slanting towards you as a result of your motion. And that's at the basis of that warping effect that you get as you're moving near the speed of light towards objects in front of you.
In reality, we don't have to travel near the speed of light to experience the distortions caused by motion through time and space. They are with us every minute of the day.
All of the distortions that happen as a result of a finite speed of light still happen on an everyday basis, even in our everyday life, but the effects are so tiny that we can't perceive them.
Still, light speed has its other quirks in the slow-moving world, quirks we perceive very well. The speed of light may be a constant, but only in the vacuum of space. When light moves through things like glass or fluids, it slows down appreciably. If it didn't, things like telescopes and human vision would be impossible. But what would happen if light slowed down much more? If the speed of light were 0? Light speed is 186,000 miles per second. It is a universal constant, but a constant with a catch. It travels at that speed only in a vacuum.
Light changes its speed when it travels through different media. It travels more slowly through water. That's why you see refraction and bending and rippling of light when you're underwater.
Life as we know it would be very different if light didn't propagate at different speeds through different materials. For example, we wouldn't be able to see. Our eyes wouldn't work the same way.
In a universe where light moved at the same speed through all materials, we would know little of the world around us, seeing only vague blobs of dark and light. That's because our eyes depend on biological lenses to focus images on our retinas. Just like lenses made of glass, they work because light slows down as it passes through them.
Well, why is that? Because light is absorbed by the atoms of glass, and then they re-radiate it later. So there's a delay factor. Light hits an atom, the atom vibrates, and then sends a light package off. So there's a delay factor.
The delay factor also causes light to bend when it hits glass shaped into a lens. Bent in just the right way, light can be focused, collected, and magnified. For astronomers studying the universe, nothing could be more important.
Thank goodness light slows down when it goes through glass, because that's the reason why we have telescopes. The reason why we have telescopes is because light bends going through glass, and we can concentrate large amounts of light to a single point, and then that gives us the ability to see the marvels in the universe itself.
Light travels through the glass lenses of telescopes at about 124,000 miles per second, 2/3 of its speed through a vacuum. But some scientists are looking at making use of light at far slower speeds.
And then we have the AOs over here. They're pretty much all functioning now.
At her lab on the campus of Harvard University, Dr. Lena Howe has taken slow light to the extreme by reducing light speed to 0.
The speed of light, of course, is incredibly high. I mean, nothing goes faster than light. And, you know, the usual 186,000 miles per second. And we kind of thought, gee, that's awfully high. Let's try to do something about it. So we have the detector right there.
Howe and her team conducted their experiments in a complex laboratory filled with lasers, mirrors, prisms, and other exotic gear. It is a branch of physics where few have dared to tread.
If you can start to change things so dramatically as taking this enormous light speed and then bring it down to bicycle speed, that then you're in a completely new regime of nature. You're able to now start to probe areas, regions of nature where nobody has ever been there before.
The brakes are put on light speed inside Howe's lab by focusing lasers on 2 microscopic clouds of sodium gas chilled to a few billionths of a degree above absolute zero. A control laser hitting the 2 clouds sets them up for action. Then, a quick light pulse shoots into the first cloud, where it is squeezed into the gas and slowed to just a few miles per hour.
The light pulse goes from being about 1 kilometer long in free space. It compresses like a concertina as it enters the atom cloud and ends up being only 0.02 millimeter in size. That's less than half the thickness of a hair. So really small, and it's so small that the light pulse actually ends up fitting totally inside the atom cloud.
Howe says the atomic imprint of light in the sodium cloud is a perfect copy, embedded in atoms, of the original light pulse. It can then be stopped in free space between the 2 clouds before moving on. When it enters the second cloud, another shot of the control laser expands it to its original size, shape, and speed of 186,000 miles per second. It is comparable in some ways to a science fiction transporter that sends people or objects through space.
So in these experiments, what we really do is we stop and extinguish a light pulse in one part of space and revive it in a completely different part of space and send it back on its way.
Since light can carry information, this super advanced technology points the way to futuristic light-based computers that bypass wires and electronic chips. Information read directly from light may be faster, more compact, and more secure than anything we have today. But the greatest vision of scientists and dreamers is to be found at the other end of the light speed spectrum. We still face the speed of light as an impenetrable wall, a speed that Dr. Einstein told us could never be exceeded. Yet history is packed with impossibles that have become realities. Will we ever, for instance, be able to reach the stars in ships that go faster than the speed of light? If so, when? In April 2008, world-famous physicist Stephen Hawking called on the human race to colonize space and make interstellar travel a long-term aim.
Spreading out into space will completely change the future of the human race, but maybe determine whether we have any future at all.
The stars are so far away that interstellar travel is impractical unless we can go faster than light speed. But that's an obstacle. Einstein's theory of relativity tells us that a spaceship's mass approaches infinity as it nears the speed of light.
So as you try to go faster and faster and faster, you actually get to a point where it takes more and more energy until it's an infinite amount of energy to go the speed of light. That's impossible.
It means that travel at light speed is also impossible. Or is it? Mark Millis is one of a handful of scientists who isn't ready to throw in the towel on the subject. A NASA propulsion physicist by profession, he likes to build models of starships in his spare time and is well aware of the giggle factor in any talk outside science fiction of star travel.
The giggle factor is actually a healthy response. It helps provide skepticism to the topic, to ask deep questions to make sure that we're proceeding correctly.
Once head of NASA's mothballed Breakthrough Propulsion Project, Millis is editor of a book that has collected the serious current research on the subject.
When it comes just to the light speed issue, there's about 36 physicists who've written articles, some skeptical, some suggesting new methods on the topic.
No one is saying that anytime soon we'll be able to have warp drive to the stars. But on a scale of centuries to millennia, it can't be ruled out.
Virtually all physicists agree it's impossible to travel through space at faster than light speed. But there may be a way to cheat by altering space instead of traveling through it.
Believe it or not, even NASA scientists are studying the possibility that perhaps we can fold space, punch a hole in space, make a subway system through space and time.
That's the basic idea behind using wormholes to actually twist space around on itself and take a shortcut through the universe. What would a wormhole machine look like? Probably huge in scale, with equipment staged perhaps on a massive number of asteroids arranged in a gigantic sphere.
It would require an enormous battery of laser beams to concentrate tremendous energy to a single point. You have to attain fantastic temperatures, the highest energy attainable in our universe, in order to open up a hole, a bubble, a gateway perhaps to another universe.
Another way of tricking space into letting us travel faster than light is the warp drive.
Miguel Alcubierre was the first one to write about the warp drive in 1994.
Alcubierre, a Mexican physicist, worked out the math for a starship propelled by warping space-time itself. Behind the ship, space-time is expanded. In front of the ship, space-time contracts. In between, the ship rides like a surfer. The ship itself sits inside a bubble, and the space around it pushes it faster than light. A successful warp drive, if it is possible at all, is probably centuries away. But in Switzerland, physicists at the Large Hadron Collider may be headed in the right direction right now.
Now, the Large Hadron Collider is an atom smasher. It's a particle collider. But it's going to get to high enough energies that space and time will actually warp and bend. We're actually practicing how to bend space in the laboratory. It's the first baby step toward a warp drive.
With the physics we now know, we won't travel faster than light speed in the foreseeable future. that doesn't mean we shouldn't try.
Even though light speed travel might turn out to be impossible, to give up without trying is just giving up.
Outside his work at NASA, Millis has founded the nonprofit Tau Zero Foundation to encourage serious research on star travel. Although few scientists are pursuing the idea actively, many agree it's worth at least the effort.
Understanding our universe is one of the most basic needs human beings have as an intelligent species. So, should we pursue technologies or physics that might allow us someday to travel faster than light? Absolutely.